An interdisciplinary approach in mathematics for classes 11 and 12, aligned with NEP 2020 and competency-based curriculum 2025-26, enhances learning by integrating concepts and methods from different subjects. An interdisciplinary approach in maths for classes 11 and 12 aim to enhance understanding and problem-solving skills. The interdisciplinary approach in teaching mathematics for class 11 and 12 promotes connecting mathematical principles to real-world situations, fostering critical thinking and encouraging students to synthesize knowledge from different fields.
Here is the application of mathematics in aesthetics, symbolism, and nature. Now, what is the golden ratio? The golden ratio is 1.618. It is represented by the Greek letter phi and is the mathematical ratio found throughout nature and art. It is defined as a ratio where a plus b divided by a equal to a divided by b. That is, a line is divided so that the ratio of the whole to the longer segment is equal to the ratio of the longer to the shorter segment. Now, applications. The Nataraja statue, shown before, often is analyzed in terms of the golden ratio. One analysis suggests that the height of the head in the statue is approximately an eighth of the total height, which is considered to be the golden ratio proportion. The second example, eyes, nose, and the art of proportion. One of the key areas where golden ratio is considered is the relationship between the eyes and the nose. Aesthetically speaking, the width of the nose is ideally 1.618 times the distance between the eyes, shown before. Some even argue that the ideal human figure has its navel at a point that divides the body into golden ratio, with the distance from the navel to the head being in proportion to the distance from the navel to the feet. The golden ratio is even applied in designing the musical instruments. One example, the violin. The ratio of violin's body length is close to the golden ratio, as shown in the coming figure. Towards the end of this slideshow, you would notice golden ratio in the sunflower seeds. The sunflower seeds are often arranged in spirals, and number of spirals in opposite direction often corresponds to consecutive Fibonacci numbers. For example, one direction might have 34 spirals, while the other has 55, both Fibonacci numbers. The shell spiral. The shell of a snail often forms a spiral that closely resembles the golden ratio. The growth of the shell also involves the Fibonacci sequence, with each chamber being the sum of the two preceding chambers.
Nature applies golden ratio in human anatomy, in sunflower seed patterns and shells, while human beings apply it in designing statues, musical instruments, buildings, etc. Where else have you noticed golden ratio in your surroundings?
Position, 15 minutes, half past, 30 minutes, quarter to, and a clock position, right? And while it runs, it tells you the hours through each spiral. There.
Wow!
And after 6.
After 6?
Because that was 7, 8, 9, just the same. So basically it's 10 o'clock.
11, 12.
Now it's half past 10, you see. This is the minutes, remember?
Integration of conic sections, symmetry, trigonometry with the concepts of physics such as force, measurement, tension, load distribution, center of mass, etc. in designing a suspension bridge. To design a suspension bridge in easy and scientific manner. First step, sketch a blueprint. Draw the top view and side view. Mark span length, tower height, cable curve, suspender placement. Next step, construct the base. Cut and shape a sturdy base. Mark tower and anchor points on the base. Next step, build the towers. Construct two identical towers using sticks or straws. Ensure vertical alignment. Next, attach the main cables. Curve the main cables between anchors. Create a symmetric parabolic curve using geometry. Fix ends tightly using hot glue. Next, build and suspend the deck. Place the deck under the cables. Use suspender cables at regular intervals to connect the main cable and deck. Apparently, the deck is looking level. Ensure the deck is slightly curved upwards in reality. Last step, reinforce and finalize the design. Strengthen with glue and supports. Add decorative elements, vehicles, lights, label parts.
The beautiful intersection of mathematics and chemistry. The concept of pH in chemistry beautifully integrates with the logarithmic functions from mathematics. pH is defined as a negative logarithm with a base 10 of the hydrogen ion concentration. That is, pH is equal to negative log H plus. This mathematical formulation allows chemists to represent extremely small concentrations of hydrogen ions in a manageable numerical range, typically from 0 to 14. Through the use of logarithmic skills, we can understand how tenfold change in hydrogen ion concentration corresponds to a unit change in pH, revealing the exponential sensitivity of chemical reaction. What is antilog? Antilog is inverse of the log. Consider the hydroxide ion solution in a basic or alkaline solution. It is represented as an exponential function 10 to the power p minus 14, where p represents pH value of the solution. Unlike acidic solution, basic solution has higher concentration of hydroxide ions, and OH minus is the concentration of hydroxide ions in moles per liter, and POH can be expressed as minus log of hydroxide ions. Consider water solution. At 25 degrees Celsius, pure water has equal concentration of hydrogen ions or protons and hydroxide ions. This is equal to 10 to the power minus 7 moles per liter. Now, at this state, when we consider pH of water, it equals 7 and is same as the pOH of value of water. So, in neutral water, pH plus pOH equals 14. How can we use this pH value used to explain a chemical phenomenon using logarithm in daily life? Fish farming. Fish are sensitive to pH. Water that is too acidic or too basic can harm their health. Therefore, maintaining a pH within 6.5 to 8.5 ensures good oxygen absorption and supports biological process. Drinking water. Too acidic content in water corrode pipes, and too alkaline water can taste bitter and cause the scale buildup. Even in the swimming pool, there is an allowable or permissible range of pH between 7.2 to 7.8. This pH range ensures comfort for swimmers and effectiveness of disinfectants like chlorine. The permissible pH range in soil for agriculture is from 5.5 to 7.5. In this range, crops grow best, but again it varies from crop to crop. Incorrect pH can limit the nutrient absorption and reduce the yield. Even in our skincare, the advisable pH value is 5.5. Since the skin is slightly acidic by nature, pH balanced soaps and lotions helps preserve the skin's barrier function. Stomach acid is one of the most acidic things, and its range is between 1.5 to 3.5. It is quite essential for digestion. Too low or too high pH can lead to acid reflux or indigestion. Household cleaning also makes use of pH. Acid cleaners help remove the mineral stains, while the basic cleaners cut through the grease.
Takeaways. The logarithmic scale helps quantify acidity and basicity precisely. Understanding log rules aids in interpreting pH changes. Students appreciate maths better when they see abstract math concepts applied in a scientific context like pH value. This interplay enhances our ability to analyze acid-base behavior, predict reaction outcomes, and maintain balance in biological and industrial systems. The synergy between mathematics and chemistry is elegantly reflected in the calculation and interpretation of pH values.
Thank you.
Integration of a concept time-based data from applied mathematics class 12 with economics in explaining inflation. Time-based data, when integrated with inflation in economics, helps students track how prices of goods and services change over months and years. By analyzing historical inflation data, students can understand the real value of money and how purchasing power shifts over time. This scientific approach uses tools like Consumer Price Index (CPI) and time series graphs to make abstract economic changes visible and meaningful. With innovations like data dashboards and mobile inflation trackers, students can now visualize trends in real time. This bridging sharpens critical thinking, showing how salaries, savings, and costs interact with inflation. It also teaches forecasting. Students can predict future inflation based on patterns and cycles. Using spreadsheets or coding platforms, learners can create their own inflation models from time based data sets. This makes economics hands on, practical, and engaging, not just theoretical. It also inspires financial literacy, helping students make smarter choices in spending and saving. Most importantly, it connects classroom learning to real world economics, making education truly empowering. Financial mathematics, as part of Class 12 Applied Mathematics, empowers students to understand and manage real life financial scenarios with scientific accuracy and logical reasoning. In a world driven by economic decisions, it bridges the gap between mathematical analysis and business planning. The subject equips learners to calculate interest, EMI, depreciation, and annuities, skills essential for both personal finance and business operations. Students apply these concepts in budgeting, investment analysis, and cost forecasting, making learning deeply relevant to their daily lives. It fosters a scientific attitude towards money management, encouraging probability distributions help us predict future outcomes like whether a customer will pay on time or how likely a product is to sell well, just like forecasting in accountancy. They turn numbers into smart decisions, helping you manage business risks with confidence. Think of it as using maths to make our business plans safer and smarter. Whether it is sales trends, credit risk, or cost variation, probability adds a scientific touch to accountancy. Learning this gives us a real edge in commerce. We are not just calculating, we are predicting the future. This graph clearly shows how probability distributions can be meaningfully applied to various topics in accountancy, making learning relevant and innovative for Class 12 commerce students. From predicting investment risks to improving sales, forecast, and audit accuracy, it empowers students with data driven insights for smart financial decision making in business and life.
Integration of dance with mathematics. Objectives: to demonstrate a collective dance rhythm inspired by Bharatanatyam that visually and mathematically represents the circle theorem and rotational symmetry. This evocative image beautifully captures six Bharatanatyam dances arranged in a perfect circle symbolizing geometric harmony and symmetry. Each dancer's position and gesture align with mathematical precision, illustrating angles, axes, and spatial balance. The superimposed symbols like the cone, integral sign, and 90-degree angle emphasize the natural integration of mathematical theorems within classical choreography. Bharatanatyam's structured rhythms, measured steps, and rotational movements reflect core mathematical principles such as proportion, symmetry, and spatial awareness. Together, the photo becomes a live canvas where the tradition and science converge, demonstrating that dance can be a visual experience of mathematical elegance.
Extension. How can we elaborate mathematical focus in the previous image? Creating steps which represents how equal angles subtended by an arc at any point along circumference. Radial and rotational symmetry. Regular polygon geometry like creation of hexagon or pentagon or septagon. And the one of the most impressive feature of dance is its dynamism, where while performing each different mathematical concepts form a beautiful spectrum for the audience. Here is another example illustrating how students can learn dance keeping in mind mathematical interpretation. Initial position: dancers stand on the circumference of a circle, arm extended outward, where arm, when extended outward in straight line, represents tangents along the circle. Angle establishment: if the arm point at 60-degree interval, then it represents the angle uh, of the angle imposed by an arc along the circle. Chakra movement. All the dancers rotate 180 degrees synchronously, creating 6 circles or 5 circles where each center is along the circumference of a common circle. Sequence repeats. 3 such rotation creates a full cycle, and then the end pause would be a symmetric star pattern. Now, capturing the dance movement also is adds aesthetic to the dance videos. Mathematics can even be applied while considering floor projection for geometric pattern, or focusing on the center spotlight for origin, or taking the photography using drones to mirror circular motions in air. This gives quite mind-blowing visuals.
Assessment and conclusion. Assessment. Peer feedback on symmetry. Mapping dance paths on graph paper. Quizzes on geometry link. Conclusion. This fusion nurtures logical reasoning and cultural expression in line with NEP 2020's interdisciplinary vision.
LIDAR is a groundbreaking technology that beautifully bridges three-dimensional geometry and physics through the science of light. It works by emitting laser pulses and measuring the time it takes for each pulse to bounce back from a surface. This time of flight is then converted into distance using physics equations, mainly distance equal to speed into time. Each measured point becomes a coordinate in 3D space, which has x coordinate, y coordinate, and z coordinate, just like in our maths chapter on three-dimensional geometry. By collecting millions of such points, LIDAR creates a detailed point cloud that models real-world environments in 3 dimensions. This process applies vector concepts to determine direction, displacement, and surface orientation fundamental to both geometry and motion in physics. The lasers follow linear paths which can be analyzed using equations of lines and planes, helping students understand abstract 3D equations in a real world context. Angular measurements and rotations in scanning systems further connect with the concepts of geometry and coordinate transformations. Under NEP 2020, which encourages experiential and skill based learning, students can explore LIDAR through project based activities like building simple LIDAR models using Arduino and sensors. They see real world use in self driving cars, drones, and mapping ancient cities, making learning exciting and meaningful. LIDAR brings abstract maths into real life, showing how what we learn shapes the future. It inspires curiosity and creativity, making students not just learners but future innovators. The orbits of celestial bodies beautifully exemplify the harmony between maths and physics, where Kepler's laws and Newton's laws of gravitation are expressed through elegant mathematical equations. Calculus, particularly integration, is used to calculate orbital paths, velocities, and areas swept over time, offering a real world application of abstract concepts. Differential equations describe how planets move under gravitational forces, highlighting the deep interdependence of motion and mathematical modeling. This synchronization enables precise satellite navigation, space mission planning, and predictions of astronomical events, showcasing math as a language of the cosmos. Students can grasp deeply and enjoy by understanding how mathematical tools interpret universe, inspire advancements in technology and exploration. Vectors in mathematics play a crucial role in understanding motion and kinematics in physics, as they provide a precise way to describe the quantities that have both magnitude and direction. In physics, displacement, velocity, and acceleration are all vector quantities, meaning they require direction to fully define the motion. For example, if a student walks 3 km north and then 4 km east, is the total displacement is not simply 7 km but a vector that combines both directions, which can be found using vector addition. This is where mathematical operations on vectors like addition, resolution into components directly support the understanding of motion paths. Velocity vectors can show how fast and in which direction an object is moving, while acceleration vectors can indicate how that motion is changing over time. Students can visualize this by plotting the movement of a car on a coordinate plane using arrows called vectors to represent different phases of motion. In projectile motion, breaking the velocity into horizontal and vertical components involves using vector resolution and trigonometric identities such as core mathematical skills. Similarly, understanding relative velocity depends on vector subtraction. Graphical methods like vector diagrams or digital simulations using tools like GeoGebra or Python can help students see these interactions dynamically. Thus, integrating vectors from mathematics into the study of motion not only enhances conceptual clarity but also bridges the abstract with the physical, making learning more connected and meaningful. Integrating Boolean algebra with hands on coding nurtures logical thinking and innovation in students. Here is a student focused explanation of the integration of Boolean algebra with microcontroller coding for class 12 computer science students. Boolean algebra forms the backbone of digital logic used in microcontrollers and all embedded systems. Microcontrollers like Arduino execute code based on logical decisions on, off, high, low, just like Boolean variables 1 and 0. Students can build simple LED circuits controlled by buttons using Boolean logic. Example, turn LED on if button A and button B are pressed. Truth tables help in visualizing all input-output combinations before programming. Boolean expressions like A and B are easily tested using digital sensors. Example, flame sensor or gas sensor for a fire alarm. Simplifying Boolean expressions helps students write cleaner, more efficient code. Logic gates and or not can be emulated in code to control motors, buzzers, or display systems. This real world application makes abstract logic tangible and fun through creative projects. This is a clear example for integration of the concepts from maths with computer science. Integration of statistics and probability with health departments during COVID-19 pandemic. During the 2020-21 COVID-19 pandemic, mathematics played a crucial role in analyzing and controlling the spread of the virus.
exponential growth models help forecast infection rates and guided timely lockdowns. Probability and statistics allowed health officials to assess risk zones and prioritize vaccinations. Logistic regression and predictive modeling enabled hospitals to plan resources and manage patient flow efficiently. Visualizing this data through graphs helped policymakers and the public understand trends, empowering science-driven decisions that saved lives.
Paraboloid in telescope reflector. A paraboloid is a three-dimensional surface generated by rotating a parabola, a classic conic section, around its axis. In telescope design, this elegant geometry is harnessed to reflect and focus parallel incoming light rays like those from distant stars to a single focal point, enabling crisp and clear imaging. This precise behavior arises from the mathematical property of parabolas, where every point on the curve is equidistant from the focus and directrix, a concept deeply rooted in both geometry and physics. Engineers and scientists integrate this knowledge using calculus to optimize surface area and reflective efficiency of the mirror. Thus, the paraboloid becomes a beautiful bridge between pure maths and practical astronomy, unveiling the universe